So welcome everybody to our first Zoom review here. These are really informal, but definitely have your chat open because there'll be various times I ask you to put something in the chat. Um, I think I'll do just 2 minutes here of general review. Our exam is Thursday. In your normal quiz section, you get a basic calculator, you get one sheet of notes front and back, and there'll be 5 pages. Homework questions are okay, but I want to focus more on exams first. So I'm going to give a little priority to that. Um, in terms of topics, typically the first 2 pages are a little more direct integration, substitution, with bounds, without bounds, simplifying. Typically, pages 2 and 3 are still integrating, but maybe some Riemann sums, maybe something graphical. um, Fundamental Theorem of Calculus Part 1 or 2, net change, total change, the absolute value stuff. And then towards the end of the exam is where I put more of the applications, meaning area, velocity, acceleration. Typically, there'll be a volume question on the last page. So that kind of, if you look at old exams, you'll recognize that structure. Um, but that's kind of a more practical collection of reviews. So can we integrate? Do we know some of those named concepts? How are we with area, velocity, acceleration, and volume? Um, so that's really all I was going to say. And then the other piece, and I'll say some of that tomorrow, is I've kind of curated this exam archive to have some of that. So work through old exams. The honors ones I would ignore. They just have a little more involved and applied, unless you finish the others. But then there's solutions. There's kind of things by topic. So I kind of think at this point, it's the student's job to kind of flip through lots of old exams and say, what surprises you? Simplifying and integrating? Is it doing the area? Is it Riemann sum notation or fundamental theorem of calculus? Is it finding plus C? So kind of think about, it might be all of them, but think about which ones are most prevalent, and we can talk about those. Cool. And I'll maybe put this. What else could I do? We're gonna go everyone in the chat. There's the exam archive. Um, Lovely. So yeah, somebody's already taken it up. What I'm gonna do for just a moment is have people start to throw things in the chat, particular questions, and I'll try to kind of keep up. And we'll do that for about 30 seconds here. And then I'll kind of look and see what this looks like. So somewhere I'm going to start keeping a list. So I see fall. Oh, I got to make these pens smaller. I had to update my OneNote. Fall 2017 question 1C. I assume that's integration. And I'm just going to note a few things here. And then I see a winter 23 2B. The slope. Okay, so it's a line, fundamental theorem of calculus question. But I know what you're asking about, and that's quick. So it will be good to clear that up. Nyana, you're looking at, sorry if I mispronounce anyone's names, question 5, A and B. So that's probably um, area volume, solving the question related to finding the volume. Lovely. Fun tangent U sub. Oh, that's what Owen's question is. I gotcha. Similar to one, could we briefly explain how to write compute volume integrals for common shapes? Not, uh, we could talk volume. So I'm just gonna make a note. Maybe other shapes. So this is kind of what I do. We do a 30-second, 1 or 2 minute collection of problems. We won't be able to do all of them, but I like this as a starting place to get a sense of a few things. And then I try to make sure we hit quite a few topics. And then this will continue into tomorrow in class. Thank you, Natalie. Question 5. Oh, overlap. Yay. Winter 2015 to be. Okay. And fall 23, 4B. And it looks like we have a few more 5. So in winter 23, 5B. Lovely. So I see maybe we'll start towards the front of my list here that isn't a line. Yeah. So I think volume's a big thing. This is a repeat of this other one. So I'm going to cross that because we have it up here. But we have volume, volume, volume. Um, and so I do want to hit that, but maybe we'll start with something else. And then we'll, in the middle of this, do a bunch of volume because that's good for us to do. So maybe let's do some 1 and 2 stuff. Just kind of hit that. At any point, you can unmute, you can raise your hand, but let's look at a problem as kind of a start. So Owen, we're gonna put you up first here. Fall 2017, 1C. This one? I think it's even without looking at it, I suspect it's an ugly looking problem. So the other thing I do whenever I open an exam, and so I like to do it in the review too, is we're going to scan through just kind of as we go. So we're trying to get to question 1, so we don't have to scan very far. But it's always good to kind of put yourself in this situation. Imagine you put your name on the exam, you kind of see the rules, and then you look at the first problems. So we might as well, while we pass problems, say a few things. So when I look at this, I think I'm going to need to simplify this. So just a comment is I immediately am going to be simplifying that. So this was not the question. I'm just going to make a couple little notes as we bypass. So do we know that there's really 5 halves of something and that this is the same as x to the negative 1/3? And I think the other thing students missed a lot on this problem, if I remember right, was this 6 threw people off. So I can come back and do that one. I just wanted to mention when I see that, I think I want to simplify. So I'm just giving you first instincts. When I see this one, I'm thinking substitution. So I love playing this game wherever I possibly can when I'm preparing for a test is first step. My first step was this, simplify. My first step here was substitution. I also know my second step, which is to take the derivative of this thing. So to me, I'm looking for things where I don't know the first step if I was preparing, and I would make sure to study that more. Very likely your first page of your exam will be sort of like that. Not exactly that, but something where you have to simplify, something where you have to do substitution. So then you get to this problem. I think I'll probably just have 2 parts on the first page. I think over the years, students said 3 parts was too much. But this just looks bad. And this is more of a lesson for later once we learn all our integration techniques. But it if it ever looks bad, it must be substitution, is the short answer. So the reason this looks bad is because of this whole mess of stuff here. So there's one fact you sort of need to recognize. And if you can recognize it, the problem becomes a lot nicer. And the fact is this. The derivative. So for I know it's substitution the moment I look at it because it's gross. But the fact that really helps me in this problem is I know the derivative of this. So somebody in the chat, I've been talking for a while now, see if you can find some way to type in what the derivative of that is. Close. It's hard to type it in. Yeah, that's it. Good. I didn't check my audio for a long time there, so I could have been talking to myself that whole time. I appreciate it. So that's what I see here is that the derivative of this kind of looks like that. And so that's the key to the problem. But that's not what we have. We don't have tangent. We have a bunch of other stuff. So I'm going to pick U to be the whole inside. So that's what I had to see. And then I'm going to take the derivative of this. Derivative of 1 is 0. This is just a coefficient. And then you all just told me in the chat what the derivative of this was. 1 plus x squared or x plus 1. Both are correct. And that's really the key to the problem. If I wanted to, so at this point now I could say the integral, all my pens are wrong, the integral of the square root of u, and the challenge becomes how do I change everything else? Okay, I'm going to write that a little nicer. So now I'd like to change everything else. I'd like to replace the dx. I'm hoping that all the x's go away. I'd like to change the bounds. Keep messing with these pens. So let's go a step sooner. Owen's answer. Oh, there's two Owens. Okay, let's go here. So if we want to get rid of the dx, you can do that in a couple different ways. But I'm going to move all of this to the other side just to show that because I did that in class a few times. So the other side is going to be, so if I multiply both sides by x squared plus 1 and divide by 12 over pi, that's the same as pi over 12. So I moved everything to the other side, and that's what dx is. So maybe that's one of the challenges. Pi over 12. Oh, the other challenge is I kind of didn't write it in a very clean way, but I still can tell that these are going to cancel. That's the key. That's the thing we had to see at the beginning. So we're really, really close to done now. So this is a perfect example of something that looks terrible, but it's simply because there's a function on the inside and its derivative on the outside. Questions on that part so far? Thumbs up if we're okay. Do we know the derivative of inverse trig functions on the midterm? How do we know du? Um, in general, so here's what I would say is put the derivatives of the inverse trig functions on your note sheet. I tend to only ask about arctangent because that's the only one that's come up in our homework. So arctangent we have seen. Thank you for your hands. I'll call on you in just a second. Sorry, I made that disappear for a moment. Let me grab this and see if I can show this. So in terms of skills, I try to keep for the first exam, I try to limit it to those. So I'm trying to keep it a shorter list. So those are the integrals I'm going to base it on. I'm going to assume everyone knows those antiderivatives. But if you know those antiderivatives, you also know the derivatives. What I'm saying is you don't really need a new list because the derivative of this is this. And so to me, I feel okay asking about that because it's in the list I have here. But if you want the full list, which is definitely worth having for kind of later in the term, let's see, am I sharing that? Yes, I am. Here, Calc 1 review. So here's kind of a more complete list. I don't usually list all 6 inverse trig because it's very rare that I've used more than just this one and this one. I did notice on a couple of the other instructors' old first midterms as I was looking at them that a few of them have arc sine, but I've never seen on any of our old first midterms anything other than those two. I like to limit myself to what you've used in the homework. All right, good question, but it isn't bad to have the full list, but trying to save you space. So if you know this collection of derivatives and antiderivatives for exam one, you're all right. Great question. There was a private question, so some of you might not have seen the question. Okay, there was a hand that popped up, or was the hand to go ahead? Uh, Okay, accidental. Okay, no problem. So in terms of finishing this, there would be two things. So one, just to show you the full transformation. Trapezoid rule won't be on the test. No, that's a private message. Sorry, if I suddenly say something out of the ordinary, I'm replying to somebody. You have to have a split personality to do a Zoom session. So I'm going to plug this in and change the bounds. Now I do know that arctangent of zero is zero. So it's one plus zero. So this becomes a one. And I'm going to plug in a one. Now, some people might say, what is arctangent? And those people would probably have to then just change back. But these two I know pretty well. This is zero. This is the way I think about this is when is sine over cosine? An inverse question is just asking you to think about when is tangent equal to one? Well, it's when sine and cosine are the same. Um, so anyways, that's how I think about it. 45 degrees, yep, or pi over 4. So at this point, we're going to turn it into u to the 1/2. It's just a long problem. I feel like I'm spending too long here. 2/3, pi over 12, from 1 to pi over 4. So from 0, did I say? Oh, I forgot something. And that's probably what's happening in the chat. Okay, not happening in the chat. Maybe you hadn't caught that yet. Well, I hadn't made the mistake yet. Well, it didn't happen. Um, this is pi over 4. But I need to then multiply that. So it's 1 plus pi over 12 over pi times pi over 4. 4. Ah, that's better. 1 to 4, 1 to 4. The homework, the 6.3 material somebody's asking is not on exam one this term. So if you're looking at old exams, you might see it, but it's not on exam one this term. For Carter saying for U sub indefinite integrals, would you rather us change the bounds or replace? I'd rather you change the bounds. This is it's a smaller thing, but if you can change the bounds, then you've changed the entire problem to be much simpler, and you never have to go back. Um, I think I might stop there because I feel like I've overstayed my welcome on this problem. But if I was doing this, they would cancel 6. I'd have pi over 18. I did some simplifying. 4 to the 3 halves minus 1 to the 3 halves. There can be revolution problems on exam one, yes. And we're going to do some of those. When I hit about 8:35, I'm going to switch over and we'll do a bunch of volume questions because I know a bunch of people were asking about that. I just felt like if we started there, we'd get too buried. Owen, can we move forward? Lovely. Thank you, Owen. Let's see, where's my little master sheet here? And I don't always do this perfectly. There are a few questions about problems too, so we are going to look. Luke had a question that I think, just based off what he said, you're not expected to show a ton of work. Um, let me look. I'm gonna go on to this question. I know there's a few questions in the chat, but winner 23. I think my this was wrong. I didn't update the date. You get two sides to your note sheet. Absolutely. And if you also, some people are direct messaging me. If you're willing to turn on chat with all, then other people can reply too. Okay, so we're gonna tour the winter 2023 exam. Pretend that we're taking the exam that term. This is winter 2023. And we have a simplification. Make it bigger. The note sheet has to be handwritten, yes. The idea is not copy and paste. If you want to write it in a iPad and then print it off, that's fine. I don't fight that anymore. But anyways, this problem I would expand, and then I'd have to remember what cosine squared is. This problem I'm going to do substitution. That's my u. This problem I'm going to do substitution. That wasn't the question. So the question was part B of this page, but since we haven't done a page two question yet, part A is actually really fast. So sorry, Luke, we're going to do part A and then we're going to peek. We'll quickly answer your part B question. So this is the bad part of my reviews is I don't directly answer people's questions. Okay. So anyways, I want to rewrite this as an integral. So let's go through the steps if this notation was bugging people. Um, Absolutely. There's a lot of partial credit to be had. I'm grading process. So if you just make an arithmetic error, there will be a deduction, but it won't be major. So that's for any questions about how much work do I have to show, the real reason you want to show work is so that you can get partial credit. So the showing work is more for you than me. Okay, so this was the setup. Delta x was b minus a over n, and xi was a plus I delta x. So when you're trying to undo this machinery, the a and the b are hiding in here. And I think there's already a question on the discussion board or in my email where somebody's saying, why is this 1 if there's an a and a b? The 1 and the n are the number of boxes. The first box, the second box, the third box. So those never change. The a and b are hiding in there. So let's play this game. So what you do is you say, well, that looks like the thickness. And so what I learned from that is that b minus a, so step one is b minus a must be 3. Done. And also what I learned from that is that this is delta x. So next, trying to undo the machinery, delta x should be sitting next to an I somewhere, and it is right here. So that's I delta x. And then sitting next to it is there's a number you're adding on. There's actually more than one correct answer to this. You could pick A to be anything you want, which confuses people. But I would typically pick it to be whatever number is sitting next to it. Some people, I've heard a few TAs when they were doing this problem, just always pick 0, which is actually also correct. But I am going to pick, so my choice, you can choose something else. I'm going to choose A to be 1. The moment I do that, several things happen. If A is 1, what's B? Tell me in the chat. 4. Owen wins the speed prize. Um, and then the other thing I like to do, just to really hammer it home so I don't make a mistake, is I label them. I say, well, if this is delta x, then what I have is xi. So I write, okay, delta x is 3 over n. This is really overkill. And xi is 1 plus 3i over n. And then I just replace. I take a moment to rewrite. So it's the limit as n goes to infinity of the sum from I equals 1 to n of the square root of xi delta x. And I feel like if I do that, then the integral becomes easy for me to write because I can see the function. It's sitting right there. Square root of x dx, and the bounds are 1 to 4. The change in x is this thing. It's actually the width of each one of the rectangles. I mean, these are not great problems. They're kind of, do we recognize? But that's one of the correct answers. Just while I'm here, another correct answer would be to pick A to be 0. And if you pick A to be 0, then that means B is 3. And that means xi is just 3i over n. And you get the integral from 0 to 3 of the square root of 1 plus x dx. Turns out both of these are correct. They both give you the same volume, same area. So anyways, identify what B minus A is, the thing that's above your N. Choose an A and then replace. How do you know it is square root of X? Oh, good. I answered it ahead of time, maybe. Um, so it really just depends on whatever you pick for your A, because you're going to write xi. Your X is going to be whatever you picked for your A plus I times whatever the delta X is. You could even pick A to be like -70, but that'd be weird. You make the limit based on the integral. We could do one, well, just to do that, and then we'll finally answer Luke's question. Um, is this, I'm going to erase this real quick. So somebody's asking Natalie, what if you had to do it in reverse? And so sometimes my answer to that question is, okay, let's do it right now on this one. So what you would do is you would do B minus A over N. So you would do 4 minus A over N. You would do 3 over N. That's your delta X. Then you'd label your tick marks. Your tick mark would be A, which is the 1, plus I times the delta X. And then right below this, you would write the square root of whatever my tick marks are. And right below that, you would write delta X. And then you say, that's the pattern for the tick marks. We're plugging them into this to get the height, and we're multiplying times the width. We're adding them up. So that's like if you wanted to type it into Desmos for you. Um, so you can see how these things align. That's the A. This is the B minus A. So this number represents how far apart these two numbers are. I'm going to move forward. We'll be asked to make a limit from an integral. There, at most, there would be one small question, probably not even worth this much. This is kind of extreme that I had this worth 5. One small question that has to do with notation one way or the other. But let's move forward to Luke's question and we'll let those other questions simmer. Um, so this one says, let me erase here real quick. The moment I see this, I know what the question is. So this is one of these questions that's about reversing, about the fact that the following two things are the reverse of each other. So if I write this, and then someone comes along and says, take the derivative, you just get back the function that's on the inside. They cancel each other off in this way. But then we learn that you can use that as a derivative rule in combination with our other rules. So that's really what these questions were. And then we did some examples where the x was on top. We talked about how you use the chain rule. Then we did some examples where the x was on the bottom. And we said the main difference is there's a negative. And then we did a couple examples in class where it was both top and bottom. And after we did those, I said, I don't ever want to do that again. Let's just use the shortcut. So the shortcut was if somebody asked me for the derivative. So the moment I see tangent of f, I know I need the derivative. We'll talk about what to do with it. That's probably, I think that was Luke's question, which is taking me forever to get there. F prime of x is, I'm going to do the following. They cancel each other off. So this is, I'm going to write down what the fundamental theorem of calculus part 1 says. So the fundamental theorem of calculus part 1 tells you how to take the derivative of an integral function like this. And it says the answer is take it and shove it in here. So take this and shove it in here. So let's do that now. So this is going to be 3x cubed. If it's on the bottom, you take this and shove it in here and put a negative in front of it. So that's the fundamental theorem. We're basically used it twice. And then there was an adjustment for the fact that the function on the inside is not just x. And so you got to take the derivative of the inside. So tell me in the chat what goes here, or my green is. Yep. So it's a chain rule. 9x squared and 2. So I'm very happy with you doing that in one step. A few years ago, I decided just to give it in a general form. So there's the general form. But you have to understand this would be a question where the variable is here and you're being asked to take the derivative. So it's actually a cancellation question. Tangent. So now I'm going to answer the second question, which is actually a review question. So this is the part that a lot of people are asking about, which is what in the world do we mean by tangent line? So here's the review. So a line, this is part silly, but a line looks like this. That's how I learned it in high school. But then later, I realized as a calculus teacher, it's better to write it this way. But whatever. In order to get the equation of a line, you need a point and you need a slope. Okay. A tangent line is a line that has the tangent slope and goes through a point. So I need to know the slope of the tangent at x equals 1, and I need to know the height of the function. And I now have access to those. So I know the x value is 1. What I need to know as well is the height and the slope. And the slope of the tangent line, that's what f prime is. So I need f prime of 1 and I need f of 1. So this was just an indirect way to ask for the derivative. The 1 is coming from the question here. Good point. Yeah. So the only reason we can do this problem is because I can now plug in the 1 to the derivative I just found. 12 over 1 plus 3 is 4 times 9 minus 12 over 1 plus 3 is 4 times 2. So I'm getting 3 times 9 is 27 and 3 times 2 is 6. So I'm getting 27 minus 6. So I'm getting that this is 21. To me, the tricky part is why can we do the integral? F of 1, that's the part that worries me actually the most. I'm like, did I mess up? But then when you look at when you plug in 1 to the original function, you get a 3 on the bottom and a 3 on top. So it's the area between the same two places. And so that's 0. So actually, I think that's the trickiest part of the problem was realizing that, oh, I can plug in 1 to the original one because it's the same bounds. Um, so the tangent line, yeah, was it means it really meant find the derivative. And then you had to use it to finish. So you had to get full points. I think the final step was worth 1 point, maybe. I mean, this was mostly was getting the 21, but that required a little bit of calculus one remembering. Did that answer your question, Luke, after a long time? How do you know to do x minus 1? That's where how do you know that the line that lines up with the tangent line? Wait, so how was the height 0 again? Good question. So there are two things to compute. I'm going to move over here just for space. So f of 1 is the integral. I plugged in a 1 for x, and when I did, it became a 3 here and a 3 here. And then f prime of 1 was that 21 we got. What do you do if the if the bounds don't equal, then you have to find the integral, and it would be a bad problem. That's why I don't ask this very often. But it appears that quarter I tried to make sure it was 0. But the comment about the one, let me think for a second. So very briefly, I'm going to pick an example that we all kind of know. Let's take a parabola. Let's go stand over here at 2. And this is just a quick review, but I want to say a few things. So I would like to know on this graph, what is the height and what is the slope? Because I want to separate that from all of this. This is not really this course, but it's something we need to know. So given the function x squared, what is the height and what is the slope? That's a key takeaway from Calculus 1. And we can compute those, they're numbers. So tell me the height from right now in the chat. We'll blow it up. So this is a totally different problem, but I want to explain what somebody asked. It's 4, yep. You get the height by plugging into the function. Now, if we hadn't taken calculus, we wouldn't know how to get the slope. So calculus 1 gave us the ability to get that other piece of essential information, which is by taking the derivative. Oh, I picked the wrong number. This was a mistake. I meant to pick the number 3. I'm going to back it up. Now, everyone already wrote in the chat because otherwise they're the same. I have a whole project on when are products and sums equal, but that's another story. Okay, so the height isn't supposed to be 9, is what I meant to say. The derivative is 2x, so the slope, now what's the slope? 6. And so the question is, how do you find the equation of a line, or how do you give the equation of a line that has height 9 and slope 6 at x equals 3? So if you wanted to actually graph that line in Desmos, you'd have to encapsulate all of this information. And that's what the tangent line does. It says the slope is 6 and it goes through the point 3, 9. If you grew up with mx plus b like I did, it takes a while to get used to switching over to point slope. But if you expand that out, you get the mx plus b form. It's sort of, I just think if you're going to find the equation of a line, a tangent line, finding the intercept is kind of weird. It's usually easier to write it this way. Does that answer your question, Luke? So the 3 or the 2 is the point. Uh, yeah, good. No, it's these little things that distract. So let's do a circle back. I know it's you have to understand we won't get to everyone's question. I'll leave everyone unhappy, but we will continue tomorrow. And this is all really good, kind of adds what we're doing. But since this is a volume question, let's switch over to volume. And we are hitting some good topics. Now we've seen a few key things. Um, so Winter 19 5 is where we're headed next. And since we're looking at Winter 19, we'll do our standard tour. So I really do think touring of exams is a thing that's great to do. Since our not all departments have so many exams. So in my head, I'm just thinking, I just want to see as many problems as I can. Simplify, substitute. Oh, okay, area between my curves, I'm going to need to draw it. So this would be, if I was testing myself, I would be thinking, do I know it's a this and maybe a line of some sort? Could I label it? Looks like that could be done with X or Y. I don't care which way. You could even, if you had time on the test, go back and do it the other way and see if you get the same thing. It's kind of cool. There's a notation one. There's a fundamental theorem of calculus, part 1, but a shorter one, much nicer than the last one. Times the derivative of the inside, but the derivative of the inside is just 1 because it's just an X. Tangent line, okay. Okay, here's finding plus C and D. Okay, that's kind of a 4-9 question. Aha! This hasn't happened yet, and we're almost to your question. But this is the one that always gets me over the years because there is a very clear step one in this problem. And when I grade exams, a lot of students don't do it. Yeah, the number one step. You don't even have to think. The moment you see those absolute values, you're solving this. And that might look bad. I always give this as an example of an equation that looks hard but isn't. This is a perfect example of a little algebra maneuver. And that's clear the denominators. My joke is always that if I put this question on the final, everyone gets it right. But if I put this question on the final, a whole bunch of people get it wrong. And so the question is, why is the second one so much harder than the first one? Because it looks weird. And so what we learn from that is if there's a fraction, clear the denominators. You can do it right away. If you're solving an equation, you never have to look at fractions because you can always multiply everything by the denominator on both sides. Ah, and then it like lifts a weight off our shoulders. And I also know step two in this problem, 1 to 4, 4 to 8. Okay, that was not your question. But I always am trying to think about this. Maybe it's my years of sports. I'm like, okay, when it comes to the game, I know what I'm going to do in these situations. I already know before the exam starts. It's really nice to take that into the room with you. Um, yep, two integrals. So then you're just going to do two integrals. You're going to do this one and this one. And the way I did it in class is I just do all the work and then at the end I interpret, try to make everything positive. I'm sure we'll do some of that tomorrow. Okay, we're finally there. So this was a question about volumes, and you're given the region between a circle. And so maybe let's zoom out a little bit and I'll draw this bigger. So here we go. Line, part of a circle. If you're on the edge of this circle, your radius is 2, it says. And if you're on this line, you have the square root of 3y equals x, or y equals 1 over the square root of 3x. I'm just kind of thinking as I go. So we have this, we have a height, we have this. Okay, so what I see in this problem, without reading any more parts, is I already know what variable I want to use. It has to do with coloring here. So if I were to say, what's the color on the right, it would be a hard question to answer because sometimes, first off, I don't know what color that is. I should use blue, maroon. Um, it's blue sometimes and red sometimes, blue or red. And the moment I see that, I decide I don't want to do that. So the mo first thing that would happen if I did this problem would be that I would mark an X right here and say that I'm going to do everything based off of X. So that's the theme I've been trying to hit on in class. So all of these, and I may not have allowed that. I don't know. We'll have to read the question. But all of these questions would start with me doing this. And that has nothing to do with the volume part. It just has to do with that I don't want to use Y because I have to split it up. Is that all right? Questions there? So that's an important first step. We're going to look because I don't know what quarter this is from. Oh yeah, like this one says use shells. So I won't ask this one. But let's hope the other ones We don't have to use shells. Okay, so now let's talk about the axis of rotation. If we use dy, we would have to use two integrals. That's true, yeah. So no matter what happens in this problem, if you do it in terms of y, there's two different patterns. There's the pattern below this line, and there's the pattern above this line. And there's nothing wrong. I mean, two problems is two problems. It's not terrible. It's just on a test, I would much rather do one problem than two problems. That's the issue. So if you were trying to do it in terms of y, you'd have to do this volume of revolution and this one. Yeah. So deciding X or Y just is there's two ways to think about it. So here's one way to do it. You could just start mowing the lawn. Walk, 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 walk. And now I'm in the region, in the region, in the region, in the region, in the region. And then look at your crossing points. Is the top always the same curve? Is the bottom always the same curve? Then X works well. So I'm just saying this again because there was another question in the chat about this. If you go this way, mow the lawn this way. Now let's look at these sides. Those are all the same, so that's fine. These are not all the same curve. It switches to something else. And so I don't want to use Y. Um, that's how you choose X or Y. Exactly what I just did. So I would choose the one where there's a clear pattern for both ends of your stopping. Yep. Yes, I have a whole video of me actually mowing my lawn. We do a lot of this in Calculus 3, and so that's more of a comment from there, but now I've stolen it for this class too. It's because it's a pattern finding thing, and there's less patterns to find here. Okay, so there's a few things we can do, and the ordering doesn't matter as much, but maybe let's just to sort of help separate our thinking. The moment I've made that choice, a whole bunch of things get set in motion. The edge of this is 2. No, we don't know what that is. Do we? Did I label it? We don't know what this is. So I know that the following. I know x goes from 0 to some unknown point I have to figure out, and I know it's dx. I know x goes from 0 to some unknown point. I know it's dx. I can label this height right here, the pattern for it. It's y equals 1 over the square root of 3x. And that's the thing that's closest to the x-axis. And I can also label the far side. I can label the far side because it's a point on the edge of the circle. And if a point is on the edge of the circle and I want to get y by itself, I can do it. Subtract the x squared. Y is plus or minus, but I want positive y's. So I'm kind of preparing the field, so to speak, preparing the space. I know how far I need to go to reach that point. It's the square root of 4 minus x squared. I know how far I need to go to get to this point. It's y equals 1 over the square. So we're learning to describe a region is really what we're doing. That itself is a pretty valuable tool. Okay. So now I still haven't even read the question yet, but I like to do all that first because most of the confusion doesn't come from the revolution. It comes from what I just did in my experience. So we chose X. We did it. So now let's read. The first one says we're revolving around the X-axis. So if I take that and revolve it around, we get a washer. And so the moment I see that, I go pi blank squared minus pi blank squared. And you actually know on the test that you're only going to get washers, so that helps. But when it comes to revolution, but it's perpendicular, that's it. So I basically have three things to fill in here. That the easier ones for me actually are the inner radius. That's what this is, inner radius. And the reason we're doing that is because we're doing big circle minus small circle. That the radius of the small circle is the 1 over square root of 3x. The radius of the big circle is the square root of 4 minus x squared. And the main challenge is to figure out where it ends, meaning you do need to know where they intersect. But I think it's not as bad as it seems because if you find the intersection of these two things, I could have done that at the beginning. Shove this in. Actually, I'm solving for x, but that's fine. Square root of 3 squared, so it's going to be 3y squared plus y squared is 4. So 4y squared is 4. So this is y equals 1. And if y is 1, x is root 3. So this is root 3. Yes. Why is it 1 over square root of 3? Yeah, because what they gave me, it's hard to see. It's kind of small there. This is what they gave me, which was partially saying, okay, you're going to need to write it the way you want. If you want it in terms of x, that's fine. If you want it in terms of y, then you got to rearrange it. The weird thing is that this is the same as the square root of 3 over 3 times x, but that's a whole nother story, that square roots can be written in so many ways. And the reason I know this is because I've graded thousands of exams and students have found every possible way to write square roots, but I don't care how you write it. Um, but there's lots of ways to write them. So that's that question. So then the next question is a variation on that same theme. So let's not worry about the intersection for now. So now I know it's this, but it's the line y equals 2. The line y equals 2 is here. That's a very different shape that we're going to get. But you don't have to visualize the shape. So to me, I go, all right, I'm still perpendicular to the axis of rotation. So it's still going to be a washer. Good question about the bounds. The bounds are not affected by the axis of rotation. The bounds are only affected by the region. The bounds represent, so the way you think about bounds and integrals is they represent the things that this variable can take on. So if you think about the problem, if I revolve up here as opposed to down below, it does not change the values of x we're plugging in. It changes what we're doing with them, but it doesn't change what we're plugging in. We're only plugging in numbers from 0 to the square root of 3. And that's why I like to label right at the beginning. Before I even look at anything else, we already know the bounds, we already know the variable. In this course, we're doing things that are all based off of some. So if you think about this problem, this entire problem is based off of first picking an x value somewhere in here. And so I really like to make that explicit. Doesn't matter what we're revolving around or anything, we're going to pick an x value and then we're going to do something with that x. Sometimes we're finding the height to get the area, but right now we're finding the cross-sectional area. So these things happen before we even talk about revolution, and it's not affected by this. What it does affect is the radius. It affects how far it is from the inside to the outside. So now we have the challenge. So the visual challenge is we have a line at y equals 2. Erase this just for space. I'm just kind of removing the things from the picture. We have this, the x-axis down here. Here's x. The inner radius is going to be what you get if you start walking and you hit the edge of the region. I'm drawing it down here because I already have made my picture so weird. So here's this. I'm exaggerating it a little bit. So the inner radius, it's hard to draw on here, but it's just that little sliver. So the question is, how far is that? Whatever that is, it's what goes here. That is what's affected by the axis of rotation. The reason I know it's a square root of root 3 is because it's the intersection of these two. So I figured out what y was. I combined and got that y was 1. Once I knew that y was 1, then I got x was square root of 3. 6, 1, and 2 can be on the exam, yes. So the inner radius is how far this is. So yeah, from here to here we know is the square root of 4 minus x squared. And from here to here is 2. So you're right, the inner radius is 2 minus the square root of 4 minus x squared. And good job figuring out a way to type that in. You can use the shell method, but it's not going to be better, especially on this problem, would be really bad. Let's just finish this with what's the outer radius, and then I want to immediately look at another one. We'll go a little over. It's just about 9, so if you have some place to go. But I want to do a few more volume questions. We did a lot of explaining there, and a lot of times when we do explaining, it makes the problem look worse than it is. And so it's nice to immediately follow up with a few more. But anyways, what's the outer radius? The outer radius is if you walk and touch the outer piece. It's from the middle to the edge of my washer. So think about what that would be. So back to our labels. This right here is y equals 1 over root 3x. And to the top is 2. So 2 minus 1 over root 3x. If you take a step back, you can see that's what got affected by changing the axis. So I don't have a, if you try to kind of guess the pattern by looking at the final result, I think that leads to trouble. It's really about labeling and then understanding what you want. Yeah, so the reason this is coming up here instead of in the inner radius is because the line is further away. So if you have an axis of rotation here, it takes longer, if you start mowing the yard, it takes longer to get out here. So that's the outer edge now. Whereas in the first problem, that was the inner edge. That's why it flipped. Let's immediately do another volume because I think it's a particularly unusual region as well. So that's, I would say, on the more complicated end. So here we go. I didn't look at the list. I apologize. Um, Here's a region. Let's rotate around the line x equals 1. So this is, this is winter 18. Apologies that I jumped past that, but I want us to immediately look at another one. So I would like you to take this, forget the thing where it says shells. Assume that I tell you this is 1. Oh, this is a homework question. I sometimes do this, just so you know. There probably will be a question somewhere on the test that's a homework question. Um, Often that's the one that people miss. So let's look at this one. So please follow up on that other question. Sorry to go. Oh, we haven't done tomatoes. You're right, Audrey. Um, but just I want to do another volume question here. If you can't read, I don't know how legible that is on Zoom, but the boundaries are y equals 3 excuse me, x equals 0, and the bottom is y equals 3. So if you um were you can use any method you want if this was on our test, but if you're using 6-2, what variable do you have to use? But either variable is fine here. But if you're using 6-2, how do they miss? What are you going to label first? You're going to label y. So the 6-2 method, and we're not doing the area right now, I'm doing the volume, is to cut perpendicular to the axis of rotation. So perpendicular. There's my scissors. And out here. I picked a terrible one because it's gonna be really hard to see. Um, but oh well. So the inner, sometimes I like to do things in a different order just to sort of emphasize here. That's the inner radius, and this is the outer radius. And that's going to be our mission in this problem is to find those. But the smallest y can be is 0. The biggest y can be is 3. So it's the integral from 0 to 3 dy. We're going to label this y. So one thing I do like to emphasize is changing the axis of rotation doesn't change anything till the very end. Let me look in the chat here. Zucchini. I don't know what's going on over here. Um, I feel like I can't drop zucchinis because students would complain about it's better if it's a small circular thing or else there's more questions. Okay, inner radius I need to know. Outer radius I need to know. But the functions always measure the distance from the axes. So when someone writes y equals 3 x to the 1/4, that measures the distance up to the function, which is not what I want. So I would need to rearrange it so that I could get this distance. It's too small the way I did it, but this little orange distance. Great question. I'm just going to detour for a second to answer this. Miso, sorry if I'm mis. Here's my question here. So here we have x equals 1. A simple note. So I'm going to draw a thin little box here. I'm going to rotate it around. And then I'm going to come down here. And I have to tell you, I became better at visualizing in 3D by teaching and doing calculus. So you can do these things without having strong visual skills. It builds over time. But if you look at this little thin box, it's touching. If it's touching, there's no hole. That's the short of it. This box here, not touching. So if you just think about that, take something, revolve it around. Yeah. So in this case, some you might say, well, it is touching right here, and that is true. But when we're doing these approximations, you have to say, are they always touching? No, there's most of them aren't touching. So if you take this region and draw this, if you revolved it around this axis, they are going to all be disks because they're all touching. But if you revolve around any other axis, it's not. Uh, so we really are turning these problems into little stick problems. We have some axis of rotation. We have some skinny little region. Ooh, what did I do? So that's actually how I think about the problems. Is it by the end of the problem, I'll have labeled X, I'll have labeled everything else, and then I go, oh, that's a shell. Now, that's not going to happen on your test, but that's how I remember, is I break it down into just one subdivision. That's part of what we're learning here is that idea. So anyways, our chore is to realize that the outer radius is 1 and that the inner radius is going to depend on the function. But what I know is that from here to here is still 1, and from here to here is the function. And that function is y over 3 equals x to the 1/4. So x is y over 3 to the 4th. That's what this is. So this is 1 minus y over 3 to the 4th. Bad part about these problems is there's no way to fake it. You have to label it correctly. You have to know what we're looking for. We will never do a volume of revolution around a slant line, unfortunately, Lucas. For years, I told students, just a slight detour, we'll do a few more problems. Um, I told students we don't do slant axis because it's not something that can easily be done. And then last summer, I ran a course where we did calculus projects. And while I was doing that, I realized I had been saying it wrong all along because you can do it one way is you can translate the whole problem. This was from that course. But I realized that there is a formula for it. And I started to derive it, and then I looked it up and I found out that it's already known. So I didn't come up with it. But I made this little project where I found the formula. It's not quite as nice, but it's the same principles. So this is don't look at this for anybody. Um, but there you go. I have a formula for the volume. It's actually, there is a mention of it in our calculus book. I then found it. So people have studied revolving around a slant axis. Um, most mathematicians, if you ask them about this, they say you would rotate the whole system and find the volume, but that messes up the function. Um, and somewhere, my crowning achievement, which I don't know what to do with, is I made a visual of this. And you can see all my craziness here. Where is it? Is that 3D? Oh, yeah. I was quite happy the day I figured all that out, but not for this class. So I made a fully animated version. I can change my function. So let's take x squared and revolve it around the x-axis. There you go. That's boring though. And now let's revolve it around some other axis. Now it's kind of weird when the axis goes through the region. Anyways, so it is possible. I'd lied for years, but and there's a formula, but we are not going to use it. It's really becomes a question of how to. It's the same story, surprisingly, maybe not surprisingly. The in order to answer the question, so I found the formula and then I was like, why does this work? I had to find a pattern for this. I had to find a way to label that, find a way to label this. I had to do a little bit of trig. It depended on the slope. But it's the same problem. It's just much harder to label. So Lucas was asking me about that. Sorry, that's a direct message I realize now, so nobody knew what I was answering. Um, but that's a side comment. So I learned something new. That's last summer. Slant axes are possible. Um, anyways. And most math people don't know that. So there's something new for you. I've asked people and they're like, I don't think it can be done. I'm like, haha. All right, so let's get back to business. So we did a couple volumes. Let's hit a couple other things. And then we can do another volume. Oftentimes, this session just sort of shows people there's more questions. Tomatoes. Maybe Sama, maybe your question's a tomato. Let's go to winter 15 or on it, winter 17. Sorry to. Are you still on here? Anika, are you still on here? I chased you away. Maybe, maybe not. I think Anika was asking about this one, which is not a tomato problem, but is like a theoretical problem. Anika, Anika, and I'm still saying it wrong, I bet. What about Salma? I think you're still on here. Winter 2015. This one? Was this what you were looking at? Or have we
It
lost?
was like one of the integral
Oh yeah,
problems.
this
Yeah,
one.
this one.
Oh yeah, this one is I remember I remember grading this test. This one did not go very well for students. And I thought the hint was helping. So if I wrote this question slightly differently, it would be a little more obvious what to do. So I don't, I learned my lesson. I think it's a little too subtle here, but the hint was trying to say, I'm, I think there's an x to the fourth somewhere because the derivative of x to the fourth would cancel this. So I was trying to say that without saying it. But I think what I did when I originally was trying to write up this question, how I came up with it, I don't know if I came up with it or saw it in the book or something, is I was like, well, this would be a little more clear substitution problem. But when you write it this way, it's kind of hidden. But there's two things. So let's just say that I gave you this, and we say that u is x to the fourth. What happens? So I think it was too hard to see that those were the same, but let's just see where this takes us. You get du is 4x to the third dx. And we'll do all our little bits of replacing. This is sort of interesting, so let's do this too. We'll change the bounds. Negative 1 becomes negative 1 to the fourth, which is 1. 0 becomes 0 to the fourth, which is 0. And this happens sometimes. I mentioned this happens occasionally. We can leave it like that. We can flop it and change the sign. Okay, let's see what else changes. U squared plus 1. So I say I don't love that problem because when I gave it, so many few students got it started. Um, but it was a substitution. And then what about the rest? Let's see if we can get everything else in there. Go ahead and replace the dx on your own and see what we get. Hoping the x cubes cancel. I got to take it one step further because there's something that happens here. So that's a success. And then we'll look at the tomato problems too in a moment. Okay, so I'm getting 1/4. I'm getting the integral from 1 to 0. So this is a successful substitution. Why is that better though? Does anybody know why we can do that one? That's the arctangent. Yeah. So this is the one we have to kind of remember, but it's this one. So we can flip the bounds or we can leave them. There's actually nothing that says we have to flip and make the top one bigger. So I'm going to write arctangent of u from 1 to 0. So the final answer is 1/4 arctangent of 0 minus arctangent of 1. Now those can actually be simplified because that's 0 and that's pi over 4. So I suspect the solutions I wrote were 1/4 of negative pi over 4 or negative pi over 16. Now you might say, I thought we're not doing an area, so it can be negative and actually makes sense. This is negative because we're plugging in negative numbers. But to me, I didn't, this problem was a failure on my part. I mean, so few students got it right because it was not obvious to choose this. So this was a non-obvious substitution problem. Um, and then you had to recognize there was an arctangent. Does that sort of answer your question? Lovely. Yes, I think I could. I don't usually say that, but I think I've already committed to it on this Zoom, and that's my intention. That's a self-imposed rule. Just for exam one, I like you to have a pretty small list of derivatives and antiderivatives. Um, for exam two, it'll expand a little bit, and I'll have kind of my official full table, which just adds a few things. At that point, you really do want to have the full list in front of you because it saves, there's a few situations. So, um, but to kind of keep practically, I don't know, 99% of the time, these are the only antiderivatives I ever use. I am aware there's a few others, but based off of kind of the history of integrals I've seen and how they're used, I feel good for exam one just saying no those. Arc sine would be the next most common, but I like being able to say there's 10. So 11, if I had to make an 11, it would be this. And that's the derivative of arc sine. I would say most of the old exams. So we'll do a tomato problem next. I'll find one. To me, the old exams hit. This is always the truth of probably a lot of courses. We tend to hit most topics uh, on most old exams. We don't hit every homework topic. The homework has the opportunity that some things you can dig into a little more. It's 5 pages of questions, usually about 2 parts a page. So there's a little more variation in integration. Like this integral is a substitution, but looks pretty messy. There's a Riemann sum problem. So one way you could like test, this is not a guarantee, but this is part of why I like to flip through lots of exams because I would think this is a simplify and integrate. This is a substitution that looks really scary. In fact, that's probably one of the harder substitutions I've had. This is a Riemann sum, so we're going to be able to rewrite this as an integral. Um, on the final, we'll have a sheet of integrals, yes, but not for this first midterm. It's just those 10. I want you to put them on your sheet. 5 pages of questions on the test. Um, anyways, there's a tomato problem question. Okay, so here we go. Let's do this one. Or this is the exam we handed out? Maybe I should do something different. Something different. This one? As I said, my ulterior motive. What are you looking for? You can write your note sheet on an iPad and print it off. Just make sure it looks like handwriting and it's normal size. so that I don't get in trouble. What can you find on the review site, Owen? What are you looking for? Exams? Fall 23 4B. Okay, we'll do that then. I should note, by the way, this is part of the reason I've been doing this. Uh, let's go here. Part of the reason I build this up is because there's no way in a session like this I can hit everyone's question, and so that's why I make all this stuff. Um, so lately I've been making a lot of walkthrough videos. This was when I first started doing that. So some of these videos are too long, I know, that no one's going to watch them, but they do have timestamps so you can hear me talk through it. Um, so a lot of these I have video walkthroughs, but it's really vital, really important we do preps. The test preps, I'm trying to give you practice, specific practice. So if you, for these ones, if you needed volume or revolution, you could try all the test prep and then immediately see my walkthrough. So in terms of tomato problems, there's some there in some of these spaces. Also, somebody was asking me about tomato problems, so I made a video where I did four of them. So later on, you could try. There's one on the winter 2015, winter 2017, winter 2018, winter 23. I did all four of those together. Um, anyways, I just that this is the first time I've kind of been putting this stuff together for this term. So you're the guinea pigs trying it out. So let's look at the question. Fall 23 and simplify and integrate, some sort of substitution, some. I don't know that we did a substitution with a twist here where you substitute and the variable doesn't go away. Um, we've got a Riemann sum. What's this one about? Okay, after something we did earlier, can you do that in one step now? Yeah, so this is asking about a derivative of an integral. So it's actually a short problem. It's a fundamental theorem of calculus part one. You're going to take your thing, your integrand. You're going to write it twice, and we're almost done. So you just have to remember, oh yeah, this is that special thing times two. Oh, not times two, 2x plus one, then times two. And then you're going to have, I don't love these questions. They were a necessary little bit of theory along the way. But that's a different question. That's not what we want. 12, that's a homework question. The area, so these are often ones that get people. Do we know enough that we can sketch an accurate enough picture to try that out? Uh, okay. This I sort of would lump in. This is not truly a tomato problem. The question's about part B, I think. But this is sort of also acceleration. At some point, we're going to have to find velocity. We're going to integrate velocity, the absolute value, but that's going to require finding when the velocity is zero and then splitting it up. Okay, so that's a sort of studying I would mix in while you're looking. Okay, so I think this was the question finally. 23. A tomato is dropped from a tall building. Okay, and we need a tomato. Let's give it some velocity here. All right, good. Yeah, dropped means, so this word right here means the initial velocity is zero. So that's why I put it kind of, so that's the hidden initial condition. So it wasn't thrown. So maybe they aren't that mad at me. I don't know. It hits the ground next to your math. Oh, this time they missed. So I'm down here. Whatever. It's going down, but it misses me. All right. With a downward velocity of 112 feet per second. Okay, so all of these questions are about flushing out what the conditions are. The calculus is sort of already done. The acceleration is negative 32. The velocity is negative 32 t. That's because they told me we're doing feet plus c. The height is negative 16 t squared plus ct plus d. So if you make the choice that the ground is zero and that positive is up, then these are your equations if you're working with feet. And we can use that initial condition. So the initial condition says that when this is zero, this whole thing is zero, and that forces C to be zero. So that actually really cleans up the problem a lot. So I can say the acceleration is negative 32. The velocity is negative 32t plus zero. And the height is negative 16t squared plus d. So in fact, if the question says dropped, then those are your equations. And I'm assuming that the start time is when we drop it. I always do that. I don't like to change the setup. It could be that you could label it something different. So now the rest of the problem, I can see the issue. I've got to find D, and they give me some other bit of information. Is everybody with me? Thumbs up. I didn't do as good a job this session getting interaction. I used to be better on Zoom with that, but out of practice. New quarter. Okay, there's a thumbs up. Hand up. Is there a question? No. Sometimes I can't find the thumb or the reactions. Um, Maybe when I'm the host, I don't have them. I should. Anyways, um, so the thing so you notice I haven't looked at this problem in years. I'm stalling. I don't know what to do, but I knew I needed to do all those things. So you can see how I compartmentalize my thinking. I don't allow myself to worry yet. Okay, now I'm going to worry. It hits the ground next to your math instructor with a downward velocity of 112. But I don't know what time that is. So I'm kind of articulating the problem. What time? I know the velocity at that time is negative 112. This does remind me, somebody asking me in office hours, why don't we say the velocity is zero when it hits the ground? This model doesn't say anything about hitting the ground. This model doesn't even know that it hits the ground. So this just assumes the tomato is going to fall forever. So we have to separate reality here from what these equations do. These equations model something dropping forever. And so the velocity when it hits the ground won't be zero. It'll be whatever they're telling me it is. Um, okay, but I don't know what time that is. There's the hard part of this question is there's a new unknown. And I've learned over the years, and I've fallen into this before, that whenever you have a new unknown, things become so much easier if you label it. I tend to use lowercase a. I realize that's kind of bad because that's acceleration, but I'm still going to do it. So to me, the problem becomes way easier with the one swift stroke of a pen here. I feel like the moment I write that down, I've got it. I feel like if I don't write that down, I'm stuck. So this is just me talking about problem solving, but labeling every single unknown and realizing there's another helps a lot. There is still, the moment I see that though, now I have two things I don't know. I still don't know what D is, and now I don't know what A is. So in total, I had three things I don't know, and I only have two facts. So then I start to think, is there another fact in this problem that I missed? Yeah. So I've just kind of, I was trying to show you how I think through it. There is one more fact in the problem that I missed. I didn't miss it. I was trying to talk through it. It's now it's impossible for me not to know these problems because I've been doing them for so long. 22,000 students, 20 years. They're in my brain forever. I'm in calculus forever. Uh, I think it's bad to do it for one quarter. Okay, it hits the ground. I have not used the fact that it's the ground. Oh, somebody already did it. Oh, that's not nice. That spoils it. Oh, and you already had it. I didn't look at the chat. Uh, I just went on and on. All right. So this was the other fact. So to me, that's I'm trying to kind of talk through. That was the challenge here. I'm also showing you there's a lot of things you could do even if you were stuck on this problem. Uh, okay, so I know that if I plug in, oh, you know, I didn't even need to label A. I'm too excited when there's problem solving because if we can get these problem solving ideas, they're so valuable forever. Um, so, anyways, labeling unknowns. So I plugged that into the velocity. I'm solving for A. A is 112 over 32. Oh, I usually have my calculator like hooked up so I can show it to you, but I did not set that up today. So 112 over three and a half. Oh, I should have known it would be nice. Three and a half ish. Three and a half is a long time. This is a really tall building. Okay. So anyways, then we're going to put three and a half in here. And we know it hits the ground at three and a half. Why did you plug A into V? So that's because they told me the velocity was negative 112 at the unknown time. So they told me two things. The fact that it hit the ground meant the height was zero at this unknown time, and the velocity is what they told me. So technically, one comment, let me just erase this for a moment. When you have initial conditions, you can effectively think right next to it, there's an equation. You take the velocity, you plug that in. This is the direct translation of what that said. And that's why that told me C. The direct translation of this was this. And the direct translation of the other condition was this. Negative 16 a squared plus c times a plus d. So if we had just written all our equations and not solved for anything, this is what we would have had. So the initial velocity was zero. The velocity at some unknown time was negative 12. And at that same unknown time, the height was zero. So this is actually what the problem said. We had to extract that information. This means that C is zero, but because C is zero, that means that A is 3.5. But because A is 3.5 and C is zero, we can get D. Does that help? Is that from A equals delta V over T? Yes. Um, I mean, it's from that's a kinetics formula, I think, way to say it. What I'm starting from is first principles of if the acceleration is negative 32, if that's our only assumption, and physicists do this too. If we assume there's only gravity and nothing else, then the velocity has to be negative 32t plus a constant, and the height has to be negative 16t squared. So this is the governing principles that lead to all those kinematic equations. It's really just one assumption. This assumption and these conditions. So if you break down this problem, we would say these are the dynamics and these are the initial conditions. And those give rise to everything else. Yeah. Anyways, so that's the theme we're getting in these problems. Um, is how do we take that and do the calculus to find our constants? Lovely. All right, maybe one more short thing and then we'll call it a night and continue tomorrow. Or maybe not. Maybe levity. It's time for levity. Okay, so that was cool. Thanks for letting me show that. Um yes, I got it. Where is this? I didn't put it on the test, but I almost had you all find the volume of this shape on the test. Does anybody recognize that? It's a sculpture on campus. At some point, I'll find the volume of it, but I decided not to put that on your test. It's the volume of the peanut that's in front of the physics and astronomy building. But the thing I was going to show, if I can find it, I got a lot of stuff here and here, here. So there's me with my lawnmower. This is just building off of today. And here is, let's get rid of the grid. And go. So there you go. Since I mentioned the lawnmower today, the lower bound is 0. The upper bound, when I stop mowing that strip, is the square root of 9 minus x squared. So yeah, I can do more subdivisions. This is for calculus 3. I could mow it in terms of y. I don't really like mowing it in terms of y, but I can. That's what we're doing. We're finding a pattern. We're just drawing one because we don't want to mow the whole lawn. And the last one in next term is polar, but we don't do that. But baseball fields do this all the time where they mow it radially. Um, a lot of out baseball fields do this. They don't mow it actually on the baseball fields. They uh, after they mow, they flatten it with a special roller. I learned to make it have the patterns. So there you go. But we'll have to learn the radial mowing next term. All right. Have a good night. We'll send that. Yep. This is great. This will be more of this tomorrow. Um, let's all ace that test. All right, all right.
Thank
Close.
you.
Thank you, thank you. Thank you, thank you, thank you. Close. Close.